Okay, so in the last video we defined some key terms with regard to chemistry. In this section we're going to get into some math. So we'll talk about units, we'll do some temperature conversions, and we'll do a few calculations with density. We're not talking about significant figures yet, so I may be following some rounding rules, but don't worry, we'll talk about those in detail later. So we're going to be using what we call SI units in this section, so or in this course, so International System Units. So um, that means mass will be in kilograms, length will be in meters, time is still time in seconds, uh, temperature will be in Celsius as well as Kelvin. We'll talk about both of those units. We really won't be using Fahrenheit at all. And then the last topic on this slide talking about moles. We'll get into that in the second section of the course. So for now, mass will still be in grams, kilograms, etc. And when you think about the metric system, the important thing to be aware of is we've got all these different base units for whatever quantity it is we're talking about, mass, length, time, etc. And then we can use prefixes like kilo or milli or centi to change the size of the unit. So here are all the common prefixes that we use. So that blue line that I made kind of in the top third of this chart, it's showing that the ones above the blue line, those are making the unit larger, right? 10 to the third, 10 to the sixth, 10 to the ninth. Whereas going in the other direction, deci, centi, milli, we're making the unit smaller, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. So you want to know these prefixes, so when you're looking at a unit in the metric system, you can figure out what it is that we're actually referring to. Really, I would say we're going to see probably kilo, deci, centi, milli pretty often, and then nano as well, 10 to the negative 9. We'll talk about that kind of in the last third of the class when we're thinking about waves and electronic structure. But those are the ones that we'll most typically encounter. Maybe micro here and there, but those are the ones you want to be aware of. Okay, so I just wanted to say a little bit about volume because volume we're going to see both in units cubed, like centimeters cubed, but also in normal volume units like liters or milliliters. So I just want to make a distinction between those. So typically you would use liters and milliliters to talk about the volume of a liquid, whereas you'd use cubed units like centimeters cubed or feet cubed to talk about the volume of a solid. So usually when we talk about cubed units, we'd say cubic feet or cubic meters, right? But what we want to do here is make sure instead that we're saying meter cubed because it's meter times meter times meter. So especially when we get into unit conversions, that'll be an important distinction to make. So what we've got here is this cube that is 1 meter on each side. So it's 1 by 1 by 1 meter. So that's what we'd say its volume is 1 meter cubed. So a meter is a little bit more than 3 feet, right? So a 1 by 1 by 1 meter cube, that would be like a really large moving box. I guess probably bigger than a large moving box, right? About 3 feet on each side. So now imagine that we take that cube and we slice it basically in every direction into 10 cuts. So going this way, we're making 10 cuts. Going this way, we're making 10 cuts. And then I can't really draw it, but on this face, we're making 10 cuts. So if I do that, I should cut it down into 1,000 smaller pieces, right? If I cut it into 10 in all three directions, I would get it into 1,000 smaller pieces. And if I do that, then that smaller fragment that I make would be 0.1 meters on all three sides, right? If it was 1 meter and I cut it into tenths in each direction, it would be 0.1 meters on each side, which would be 1 decimeter on each side, or 1 decimeter cubed. So if ballpark a meter, and I'm using American units just in case those are more comfortable for you to kind of eyeball, ballpark, if we think our 1 meter is about 40 inches, then this little cutout that I've made that's 0.1 meters on each side, that's like 4 inches on each side. So 4 by 4 by 4, if you're kind of trying to think about how it might look. And here is a time where we're going to see the relationship between cubed length units and volume units. So 1 decimeter cubed is equal to 1 liter. So now we see how the volume units are going to converge. If I repeat the same process we just talked about, so cutting in all directions in 10 cuts, then now I would have the smaller square that I get out would be 0.01 meters on each side, which is 1 centimeter. So now if I have a 1 by 1 by 1 centimeter block, that's the volume that's equal to 1 milliliter. So all that being said is for us to acknowledge 1 milliliter equals 1 centimeter cubed, 1 liter equals 1 decimeter cubed. So the base unit of length, meter, doesn't directly convert into the volume unit. It's decimeters cubed that converts to liters. And that's probably just logical because 1 meter cubed is a giant volume, so it's probably not a very logical base unit for volume. So anyway, that's something that you'll see when we're talking about volume of liquids. We'll use liters and milliliters. When we're talking about volumes of a solid like a block, we'll be using cubed units. So we're talking about volume so much because we're going to get into density a little bit later. Before that, I'm going to talk very briefly about uncertainty here, but we'll deal with it in more detail later. Then we'll do some temperature conversions, and then we'll talk about density. So something to be aware of, particularly in the lab, is when you're doing measurements, you're going to have different degrees of accuracy depending on what vessel you use to do the measurements. So in the first experiment we typically do in the lab, that's one of the things you figure out is the relative accuracy of different devices. So this is just showing a whole bunch of different things we can use to contain liquid in terms of measurement. So most commonly we'll use something called a graduated cylinder, which is exactly how it's described. It's a cylinder with a bunch of gradations, a bunch of markings on it to accurately measure whatever volume it is you want. And there's all sorts of different sizes depending on what you're doing. Typically more accurate than that would be a syringe where the gradations are in smaller increments. Something else that we use for titrations, where we're trying to add a very accurate amount of one substance to another, is something called a burette. So this burette has a valve on it that we can open and close to regulate the flow of liquid. And again, it's narrower than a graduated cylinder and has a lot finer markings on it, so you can very accurately see how much liquid you're adding to something. A pipette is another accurate way to measure liquids. And then lastly here, a volumetric flask, which essentially has a marking somewhere on it, and we're told if we fill the liquid to a particular height within that volumetric flask, then that's the volume that we'll have. So we use those to prepare solutions, right? So you'd add some solid to it, cover that solid with liquid and then shake it around to dissolve. and then top off the liquid so it fills uh, to that line to get exactly the volume you want. So that's for preparing solutions. All right, so we'll come back to the uncertainty stuff when we talk about significant figures, probably in the next couple videos. For now, all I want to do is a little bit of temperature conversion stuff. It's probably been a while since you've thought about doing temperature conversions, but in chemistry, we're just going to be talking about Celsius and Kelvin. So we'll do Fahrenheit Celsius conversions and Kelvin conversions, but going forward, our units of temperature that we're going to talk about are not going to be Fahrenheit. Okay, so very briefly here, right, here's 32 Fahrenheit and 212 Fahrenheit, the freezing point and boiling point of water, which correlates to 0 degrees Celsius and 100 degrees Celsius. So what we see is a range of 100 degrees on the Celsius scale correlates to a range of 180 degrees on the Fahrenheit scale. So that gives us this 1 to 1.8 ratio, or maybe what you're more familiar with is 9/5. That's the same as 1.8 ratio for degrees on the Celsius scale relative to degrees on the Fahrenheit scale. So that's why you'll see 9/5 or 5/9 in the conversion equation between the two. The one that you may not be familiar with here is the Kelvin scale, and it's also 100 degrees of interval, so it's the same degree to degree ratio as the Celsius scale, but the point of the Kelvin scale, and we'll talk about this more later probably, is it's set up so that Kelvin will never have a negative temperature. So as best we know, the lowest achievable temperature is negative 273. So if we say that 0 Celsius is 273 Kelvin, then we'll never be able to get to a negative Kelvin temperature. And for reasons semi-unknown, we don't say degrees Kelvin like we say degrees Celsius. We just say Kelvin. I don't know why that's the case. Something to think about more broadly and not that critical right at this moment is when we think about what temperature is, it's a measure of the average kinetic energy of the particles in a sample. And simply put, right, when we're at a higher temperature, we're going to observe that particles are moving at a greater rate of speed. So kinetic energy is related to the motion of particles. Okay, so I think I already said this, right? We're going to be thinking about Celsius and Kelvin scales, not Fahrenheit. And I think, like we said, 0 Celsius is freezing point of water and 100 Celsius is the boiling point of water. That's the basis of that scale. And with Kelvin, officially, this is our conversion equation to go between Celsius and Kelvin, or vice versa, 273.15. And Kelvin, like I said, the purpose of it is to ensure that we never have a negative temperature. That's important for mathematical calculations, but it's kind of based on studying the properties of gases, which we'll talk about second to last towards the end of the class. I already said Fahrenheit scale is not used in scientific measurements, so we'll do some conversions just for practice with that, but every thermometer, every measurement we're going to do will be in Celsius. So here's that 9/5 or 5/9, depending on which direction you're going in. So the top equation is if I have a Celsius temperature and I want to go to Fahrenheit. The bottom equation is if I have a Fahrenheit temperature and I want to go to Celsius. So old news, presumably, but just kind of want to get you back in the swing of things with some unit conversions. Okay, so an example here. So I think I told you this before, right? I'm just scrolling through the PDF so that I can mark wherever I want and kind of fill things in as needed on the slides, which sometimes means there's already going to be a solved example on here. So if you're following along with the PowerPoint, you're kind of clicking through this part here, or you can just see it all at once. Anyway, the question here was to change 172.9 Fahrenheit to degrees Celsius. As I said, we're not worried about significant figures yet. I'm vaguely following some of it in these examples, but we're not worried about it yet. So this equation here is showing what I would do if I had Celsius and I wanted Fahrenheit. That's not what we want, right? We want to rearrange the equation. So subtract 32 from both sides, multiply both sides by 5/9, and then here's my equation. If I have Fahrenheit, how to get Celsius. And so we plug in our given value of 172.9, subtract 32, multiply by 5/9, and it tells us that 172.9 degrees Fahrenheit is equal to 78.3 degrees Celsius. Okay, so I think I have 3 of these to go through. So this is kind of the format of how things will go in general, that we'll talk about a concept, I'll show you an example problem that's already been worked out, and then if we were in the classroom, right, I would put these up and have you guys work on them, and then we'd go over them in a few minutes. So you can either just keep going through the video and watch me solve them now, or if you like, you can go ahead and pause the video here, work through these on your own, and then come back and then verify that that you've done them the same way that I have. Okay, so the first one here, I've got the opposite of what was in the previous one, right? In the previous one, I had Fahrenheit and I wanted Celsius. Now I have Celsius and I want Fahrenheit. So we know degrees Fahrenheit is 9/5 times degrees Celsius plus 32. Let's just say 32.0. So I have what I need to do that, right? It would be degrees Fahrenheit equals 9/5 times 35.3 plus 32.0. Find my calculator real quick. Okay, so I'll call it 95.5 degrees Fahrenheit. Okay, so like I said, probably pretty old news, but hopefully that makes reasonable sense. The next one, we've got 25 degrees Celsius, and we're just trying to change it into Kelvin. 25 Celsius is a pretty common temperature that we see in chemistry. That's like 78 Fahrenheit, more or less, so kind of warm, but that's what we call room temperature for the sake of chemistry a lot of the time. Well, Kelvin to Celsius is pretty straightforward, right? Kelvin is just the Celsius temperature plus 273.15. Again, we're not worrying about significant figures yet. We'll get to that probably in the next video. But that's straightforward, right? I would just plug in 25, add 273.15 to it, and that gives me 298.15 Kelvin. Really, I just wanted to make you feel comfortable with Kelvin and all that, but this 298 temperature, that's room temperature in Kelvin, so you'll see that value come up a fair amount when we start doing calculations with temperatures in Kelvin. Okay, hopefully so far so good. And then one last one of these where now I've given you a Fahrenheit temperature and I want you to go to Kelvin, so keep in mind you can't do that directly, right? I'm going to need to go from Fahrenheit to Celsius and then Celsius to Kelvin. Okay, so then to get degrees Celsius, right, it will be 5/9 times the Fahrenheit temperature minus 32. So I can do that fairly easily, right? Okay, let's see what we get for that. I'll call it 50.6. So I'm not being very cautious with rounding yet, just because we haven't talked about it, but we'll get there. And so then now I want Kelvin, right? And Kelvin is Celsius plus 273.15. So it's going to be 50.6 plus 273.15. So I guess we can call it 323.75 Kelvin. And again, like I said, when we talk about significant figures, we'll be more cautious with all this. Just don't want to get into that right now. Okay, so some basic temperature conversion stuff just to kind of get you into the unit conversion business. And hopefully that all feels pretty okay so far. So now we're going to shift away from the temperature conversions, and then I think the last topic for this video, we'll do some density calculations. This is something you'll see a fair amount of early on in the lab course as well, but it's a good opportunity to start to get comfortable working with units. So we know that density is a physical property, right? It just requires us to measure the mass and the volume. So it's not changing a substance into anything else. The units could vary depending on what mass unit we use and what volume unit we use as we're doing this, but that is the ratio that we have. And because it's a ratio of mass and volume, we know that it's also an intensive property. Okay, so some example calculations of some of the things that we want to be able to do with density. So the first problem is kind of just following the definition of density. So it's a 525 milliliter sample of an unknown liquid. It has a mass of 375, and it's asking us to determine the density in grams per milliliter. We have grams and milliliters, so nothing to worry about with units. So really, we're just using the definition of density, which is mass over volume. So we just plug in the mass that's given, plug in the volume that's given, and doing that division, we get that the density of this liquid is 0.714 grams per milliliter. So that's what we call a compound unit, right? It's made up of two different units. That's what density is going to be. Notice it's a liquid, right? So the volume is in milliliters, not in a length unit cubed, like it will be for the next example. So this is just two examples kind of sorting out based on the definition of density, how we would use mathematical information to figure it out. Okay, so what's going on in the next one? 425 gram piece of an unknown metal, so now it's a solid, has dimensions of 8 by 4 by 2 centimeters, and we want to figure out the density in grams per centimeter cubed. Okay, so I've got this rectangular prism, presumably that's 8 by 4 by 2, so we need to know to get the volume of that, it'll be length times width times height. So 8 times 4 times 2, and it's centimeters times centimeters times centimeters, so it's going to be centimeters cubed as the unit there. And that's part of why I want you to get in the habit of saying centimeters cubed, feet cubed, not cubic centimeters, not cubic feet, because the unit itself is actually cubed, and that's going to matter when we get into unit conversion. Okay, same plan here, right? We know density is mass over volume. We've got both of those values, mass, volume, so we plug them in and divide, and it tells us that the density of this particular solid is 6.6 grams per centimeter cubed. Okay, so those are some examples to start with, and then I think I have a couple problems for you guys to work on. So same story, if you just want to keep going with the video, that's fine. If you want to pause me and work it out yourself and then check that it works out, along with me, that's fine too. So let's see what's happening here. There are two unrelated questions, but both talking about this particular liquid. So it tells me that the liquid has a density of 0.875 grams per milliliter. And in the first question, it says, what would be the mass of a 25 milliliter sample of this liquid? So that's the first question. So let's see what's going on with that. So we know that density equals mass over volume. And in this first question, it's asking me to solve for mass. So I'll rearrange my equation first. So that means mass equals density times volume. So I have both of those quantities. So if I want to write the density, I can write it as 0.875 grams divided by 1 milliliter. And then the volume is 25.0 milliliters. Okay, let's do this multiplication. And I get, we'll call it 21.9. Oops, that's not 21.9. 21.9 milliliters. So density is a good opportunity to just get comfortable with the equation, right? It's clear how to rearrange to solve for whichever parameter we're looking for, but it's also a chance to start to see how unit conversion is going to work and how we can cancel out units. Oh, I wrote milliliters and it should have been grams. Whoops. Sorry, a couple of mistakes in my first days of videos here, but I'll get back on track. All I wanted to show you here is the milliliters in the denominator of the density cancel out with the milliliters here, which are technically in the numerator of that value. That'll be a fundamental concept we'll see going forward, that I can cross-cancel units just like I can cross-cancel when I'm multiplying fractions, for example. Okay, so that's what's going on with the first one, and I rounded to 3 total digits. That's where I got 21.9 from. We're not worried about that yet, but technically that would be the correct rounding for multiplication. Okay, the second part is not related, right? Now it's saying what would be the volume of a 78-gram sample of this liquid? So starting with the density equation, now I'm trying to solve for the volume. So we saw we can multiply both sides by volume and we get mass equals density times volume. But now I want to get volume by itself. So now I divide both sides by density and I'd get volume equals mass divided by density, which I'm going to think of as mass times 1 over density. So this is just working with the equation to kind of figure things out. So we'll do more or less the same thing as before, set up our calculation, and then I'll also show you how the units work out. So volume equals the given mass, 78.0 grams, times 1 over the density. So the density is a conversion factor, right? I can either go from grams to milliliters or from milliliters to grams, depending on what it is I'm trying to do. So rather than writing 0.875 grams over 1 milliliter, I'm going to write 1 milliliter over 0.875 grams. So I'm following what the equation tells me, right? Volume is mass divided by density, but we'll also see how the unit cancellation works out. So 78 divided by 0.875 gives me 89.1. And that's going to be in milliliters. And so same idea, right? I can see that grams in the numerator of my initial unit cancels with grams in the denominator of the density, the way I've written it upside down, so it leaves me with milliliters. Okay, hopefully that's all making okay sense. One more of these to do, and then we'll call it on this video. Okay, let's see what's happening here. A solid has a density of 4.75 grams per centimeter cubed. Determine the volume of 855 grams of this solid. The second part is a follow-up to the first part, so let's see what we can do with the first part. So density equals mass over volume, and then we saw we can rearrange that to make it into volume equals mass over density, which I wrote as mass times 1 over density. So same thing we did on the last one. So we can start with that. So volume equals 855 grams, that's the mass. And then the density is 4.75 grams per centimeter cubed. But I want to flip it around, right? So it's going to be 1 centimeter cubed divided by 4.75 grams. So let's check this one. Okay, so I get 180, and it's volume, so it's centimeters cubed. And also, we can verify that the units cancel out, right? Grams go with grams, so I'm left with centimeters cubed. So again, I like density as an initial example of unit conversion because the equation tells you what to do, but if you follow the units through the equation, you'll see that they will cancel out appropriately. Okay, let's see what's happening in the second part. So now it says, if this solid is a rectangular prism with a length of 10 centimeters and a width of 9 centimeters, what is the height of the solid block? So we saw earlier, right, and this is hopefully old news, length times width times height equals volume. So now I have length and width and volume, and it's asking me to solve for height. So fairly straightforward, right? That would just mean height equals volume divided by length times width. So we can follow that fairly easily here. It'll be 180 centimeters cubed, and then the length is given as 10.0 centimeters. I'm just using parentheses for clarity, and the width is 9.00 centimeters. So now here we're able to figure out the height of the block by taking volume divided by length divided by width. And in terms of the units here, right, the centimeters cubed is divided by centimeters squared, so it'll just be centimeters that we're left with, which is good. That's what we'd expect for the height. And if we solve that, we find that the height would be 2.0 centimeters. Okay, so we did a little bit of conversion with temperature, a little bit of conversion with density, so it's setting us up to get more into the conversion business. And I guess we started by introducing the metric system as well. So yeah, let me go ahead and stop here, and then we'll, in the next video, we'll start to get into significant figures and rounding rules and all of that stuff, so we're appropriately reporting our mathematical answers. But yeah, I'll go ahead and stop here.